Okay, hello everybody and welcome. Hopefully my Kiwi accent is not too strong and you can understand me. My name is Andrew Dine and I'm a member of the Solenis team who has been working on developing our geothermal power technology portfolio over the last few years. In my spare time, I'm also the commercial lead for Solenis operations in New Zealand. I want to thank you all for attending and investing some of your valuable time today to learn about some exciting developments we have been working on for scale control and geothermal power systems. Today's webinar will consist of two presentations on the modelling, monitoring and control of the two most challenging deposit species found in geothermal power, those being calcite and silica. This will take approximately 40 minutes, leaving 20 minutes for questions and further discussion. Today's session is being recorded and the recording will be available on solenis.com within the next 2 to 3 days. I want to ask that you please ensure your microphones are muted, and also if you could please hold questions until after the two presentations, and we ask that you submit these questions via the Microsoft Teams meeting chat function. You're also very welcome to contact us at any time after today's webinar, either by my email, which I'll share a little bit later on in the presentation, or through solenis.com. Before we get underway with the presentations, a very quick introduction to Solenis. Solenis is a global specialty chemical company that has been adding value to both consumer and industrial markets for over 100 years for its various legacy organisations. And I'm sure many of you may be familiar with brands such as Drew Industrial, Betts Laboratories, Hercules, Stockhausen, Ashland Water Technologies, and most recently the BASF Paper and Water Division. We're very proud to be leaders in our strategic markets, and we operate globally in 120 countries, employ some 6,000 people, and produce our technologies from 47 manufacturing plants across 5 continents. Our reason for existing is to solve tough water treatment and process improvement challenges through the core elements of people, experience, and technology. And by doing so, we help our customers meet their operational and sustainability goals. I want to say very clearly that the geothermal power industry is very much a strategic market for Solenis. And over the last 3 years, we have carried out extensive voice of customer research, and we've invested over $2.5 million in R&D to develop solutions to the problems and challenges that have been highlighted by the industry to us. As a result, we've developed and validated a portfolio of novel and industry-leading technologies, some of which we're excited to be introducing to you today. Today's first presenter is Dr. Mike Bloomley, who will be covering calcite management and control. Mike is the group leader of Solenis Water Applications Laboratory in Wilmington, Delaware. Over the past 3 years, Michael and his team focused on the research, development and commercialization of new calcite scale inhibitors and online cleaning methods for geothermal power producers. Additionally, Michael regularly provides technical modelling support for geothermal, cooling water, reverse osmosis, and mining applications around the world. Michael has a bachelor's degree and a master's degree in chemical engineering from Case Western Reserve University in Cleveland, Ohio, as well as a doctoral degree in chemical engineering from the University of Minnesota in the Twin Cities of Minneapolis and St. Paul, Minnesota. So a pleasure to hand over to you, Michael.
Thank you, Andrew, for the introduction. And thank you all for attending today. So I'm excited to share and discuss with you some of the work that Solenis has completed over the past several years concerning scale control in geothermal power plants. As Andrew mentioned, I'll be focusing on calcite scale deposition and scale control, and then I'll hand it over to my colleague Peter Slipe, who will focus on silica silicate scaling. So scaling can occur in many parts of a geothermal power system, but calcite deposition typically occurs in production wells and steam separator equipment. Calcium carbonate deposition in untreated or poorly treated systems can lead to rapid plugging of production wells and surface equipment, as is shown in the picture here on the right. Ultimately, this can result in fewer megawatts of power generation for the power plant. However, the process and chemistry that lead to calcite deposition is pretty well understood. In many production wells, flashing occurs in the wellbore. This flashing increases the pH of the brine and increases the ion concentrations in the brine, which can lead to rapid localized deposition, as shown in this picture on the right, and then shown schematically on the left here, where in the wellbore, flashing occurs at these depths, and then schematically we've shown these deposition points shortly after the flash point. Since we understand the processes behind calcite deposition, we can model them pretty well. One thermodynamic modeling program that has been used widely in the geothermal industry for over 40 years is WATCH. This is a very powerful program, but it's a standalone application that has to be installed on your computer. It can be quite time-consuming to use, and it lacks some charting capabilities and other user functionality. So one advancement that Solenis has made in the past year or so is the development of a web-based user interface for WATCH, which we have called the GeoSol Performance Modeling Tool. By using this web-based interface, users can quickly navigate through simulations and look at the likelihood of scaling in either existing or proposed production wells. Additionally, this free tool can be used by any users, including those outside of Solenis, and it can be accessed off of Solenis's website with the link shown here. So again, this is a free tool open to everyone. And with this tool, we can model calcite saturation indices and look at the likelihood of scale formation in production wells and surface equipment. So in this example here, we're plotting calcite saturation as a function of flash temperature, and at values greater than 0, we are supersaturated, and when we get above a CSI of 0.5, then we're really likely to form scale. So now that we've talked about some of the basics of calcite formation, what do we do to prevent it? Well, one technique that has been widely employed with success is to use capillary dosing systems to apply an anti-scalant, which is shown here on the left. So we have our capillary dosing system that goes into the wellbore, and we want to ensure that we're adding the anti-scalant below the flash point. Now, when we consider anti-scalants, there's several factors that we want to keep in mind. One is thermal stability of the product, especially for high enthalpy wells. A second one is a tolerance for the brine chemistry. And one area that Solenis has really focused on is the impact of metals, such as iron and aluminum, on the performance of anti-scalants. We've heard from customers around the world about examples where they have calcite carbonate formation, and in many cases we believe this is due to underdosing of the anti-scalant chemistry because the poisoning effect of metals in the brine was not included. And lastly, of course, the anti-scalant needs to be high performing and highly effective for calcite inhibition. So within Solenis, we saw an opportunity to spend some time focused on calcite inhibition. And over the past 3 years, we've done synthesis, characterization work, and the development of commercial products, which I'll share some information with you right now. So we have conducted quite a bit of laboratory testing internally within Solenis. We've looked at over 30 commercial and developmental products, and we've also benchmarked it against chemistries that are currently used in the industry. So in this example here, we have developed our own in-house thermal stability testing, which is summarized on the bottom left, and I'm providing some example data for calcite inhibition performance at multiple dosages of our anti-scalant product. So inhibitors A and B are benchmark chemistries, and with increasing dosage, we see increasing performance, but we also see that there's a large change in performance between the lowest dose of 1.5 to the next dose of 5. So really, you need to get above a minimum dosage to see a high degree of performance. Now, if we compare this to some products that Solenis has developed, these are labeled C, D, and E. We can see that we have some comparable or even better performance, especially with inhibitor C in this testing. And so after extensive lab testing like this, again, we have found products that are thermally stable and provide superior calcite scale control compared to benchmark chemistries. Additionally, we've worked with third parties such as GNS Science in Taupo, New Zealand, to conduct their own lab testing of our anti-scalant products. So they utilize a NACE test, which you may be familiar with, and they have their own thermal stability testing protocol, which includes heat treatment at 300 degrees Celsius for 4 hours. So pretty extensive thermal aging. So here we're comparing calcite inhibition for products without thermal treatment to those that have been heat treated at 300 degrees Celsius. And again, we have our two benchmark chemistries, A and B, and we're comparing them with our Solenis products, C, D, and E. So again, that product C from the previous slide looks very thermally stable, has high performance. Product D also gives pretty good performance even after thermal treatment, but with this more stressed thermal treatment, we do see a little bit of a difference between the unheated and heated conditions for inhibitor E, suggesting that this would be a product that could be used in lower enthalpy wells, but we would not want to use it in very high enthalpy wells due to potential degradation of performance. So previously, I mentioned the impact of metals on calcite inhibition, and this is also an area that we've spent some extensive time looking and quantifying in the laboratory. So again, aluminum and iron are common metals in many geothermal brines around the world. One overlooked thing is the impact of these metals. They are known to poison many chemistries that are used in anti-scalants, and ultimately can reduce the overall effectiveness of the anti-scalant. And so if we know that impact and we can quantify it, then we can account for it and increase our dosing accordingly and make sure that we're not underdosing and ultimately leading to calcite deposition in the production wells. So in this particular example here, once again, we're showing calcite performance at 3 different levels of aluminum concentration. We've got a Solenis GeoSol product, GS9200, versus that inhibitor B benchmark chemistry. And not only does the GeoSol GS9200 product have better calcite performance in the absence of aluminum, but you can see that it maintains that performance even in the presence of 1 ppm of aluminum. And again, through this type of testing, now we know how to quantify it and account for it in our modeling. Similarly, testing has been done with iron, and we found a very dramatic impact of iron in our testing. So I have a different product shown here, GeoSol GS9220, and comparing it to that inhibitor B chemistry once again. You can see in the presence of 1 ppm of iron, the inhibitor B has almost no calcite performance. It's down to about 10% compared to the baseline for GS9220. So GS9220, there's some loss in performance in the presence of iron, but again, it is a more metal tolerant chemistry. And again, now we know how to quantify it and account for it. So putting all this together, we've commercialized several calcite inhibitor scale products and taken them to the field. So the first case study I have for you is from New Zealand in a geothermal binary plant. In this particular case, there was about 0.6 ppm of dissolved aluminum in the brine, and we used our GeoSol performance modeling tool to model this system and pick an anti-scalant that was thermally stable and had good aluminum tolerance. And then using our modeling program and our knowledge, we could estimate a calcite inhibitor dosage. So in this particular case, we came up with a dosage of 4 ppm. 3 ppm was based off of the calcite saturation index of the brine, and then we needed another 1 ppm of product to account for that aluminum that was present in the brine. And this 4 ppm did represent about a 33% reduction compared to the incumbent product that the customer was using. So ultimately a potential cost savings for this particular customer. The second case study I'll share with you is from Central America. And this is a case that we worked very closely with the customer, Ormat, and it ultimately resulted in a paper that was recently published at the GRC just last month. So Ormat was really struggling with rapid calcite scaling in their production wells. It resulted in a loss of 3 megawatts of plant capacity, and they required mechanical cleaning on a pretty regular basis to remove that calcite. The product that they had been using just wasn't working. We suspected it was due to poor thermal stability, but this was also a very challenging brine that had about 1.7 ppm of aluminum. So once again, we utilized our GeoSol performance modeling tool to model the system, and using the lab screening process that I mentioned previously, we chose a product that had good thermal stability and good aluminum tolerance. So here we have some data where calcium concentrations were monitored over the period of several months. So the blue dots are with the GeoSol anti-scalant applied, and the orange dots are without the anti-scalant. So in these bump tests, you can see that there is a difference in the calcium concentration, indicating that the anti-scalant is working. And additionally, Ormat monitored wellhead pressure, brine flow rates, and they all went back to pre-scaling conditions, indicating that the well was staying clean. And then ultimately, Ormat did some subsequent well surveys and found that the wells were very clean and that the anti-scalant was highly effective for prevention of calcite deposition. And this customer's been using the GeoSol product for 9 months now without any issues, and again with much greater superior performance as compared to the incumbent product. With that, I thank you for your attention, and I'll turn it over to Andrew to introduce our next presenter.
Thanks very much, Mike. We would ask, as I said at the beginning of the meeting, that if we hold any questions, please, until we finish the second presentation, and Mike will be happy to answer any questions that you may have at that time. Our second presentation will be presented by Peter Slipe, who will be discussing silica deposition monitoring and control. Hold on a minute, Pete. I'll just give it to you. And Pete, if you'd like to go to the next slide. I've got it. Here we go. So Peter Slipe has more than 30 years of water treatment experience and regularly provides consultation support to customers around the world in a variety of industries, including power, geothermal power, metals, and chemical processing. During the past 3 years, Peter played an instrumental part in advancing Solenis research and development efforts in scale and corrosion control for geothermal power process. Most recently, he moved into business development at Solenis with a focus on the New Zealand geothermal power industry. Peter has an undergraduate qualifications in chemistry from the University of Auckland in New Zealand. So Peter, it's a pleasure to hand over to you.
Thank you, Andrew, and good afternoon, good morning, good evening, everybody. I know I'm feeling for my colleague Mike, who's it's early in the morning where he is, whereas I'm here in the early evening, which is much nicer. So yeah, thank you, Andrew, and thank you, Mike, and welcome everybody. Now I'm going to be focusing on this, assuming my control works okay. I'm going to be focusing on silica and silica deposition, as Andrew has indicated. Just making sure I can advance the slides, which doesn't seem to be working for me, Andrew.
I can take over for you, Pete.
Yeah, please. I'll just ask you to move us forward. Okay, so look, and what I did want to say a couple of things. Now, some of the people who've joined perhaps didn't hear the start of Mike's presentation, where we were discussing calcite scale formation and how the chemistry of calcite formation is actually pretty well known, and it can be modelled quite well as well. Well, I've got to tell you, silica is not that well known, and it does throw us some difficult problems from time to time. But as you'll hear when I talk about the developments that we've worked on here, we do have something quite new and interesting to discuss with you. So if we start with silica deposition, and now what I'm talking about here is in a geothermal power station or system, is if you actually find deposits and you analyze them and they've got high silica, right? Now that will be the classic. So the classic silica deposition is what we'll be focusing on. And largely that's amorphous silica. So when I'm talking coming up about silica deposition, really talking about amorphous silica, and I'll describe that just shortly. But okay, silica deposition, where does it occur? Well, you can actually get it in production wells, especially in high enthalpy wells where the actual brine that's flowing into the production well is actually already a mixture of steam and water. And you do get like a flashing, micro flashing in the formation, and you get silica deposition there as well. Certainly up in the separators where you first get like a sudden change in pH, and you get a concentration increase and some sudden cooling. That's obviously going to be a place where you get deposition, and you can get all sorts of deposition there, including deposits with high silica. And then in binary heat exchanges, and in particular, of course, as you're taking heat out of the brine, it cools down, the solubility of silica reduces, and there you can start things happening with silica as well, and silica deposition. And then certainly, and very importantly, in the reinjection system, which is the coolest area, of course, and including the reinjection wells. So we've got time there. You know, sometimes it can take 20, 30 minutes for brine to actually leave the actual plant. So it's already cooled down, it's already saturated or super saturated, and then things start happening. And then on the way down to the reinjection, we can certainly get silica deposition there, and also in the receiving formation. So right through the whole system, but especially where things start getting cold. Thanks, Andrew. Okay, so some pictures of silica deposition, what it looks like, and I'm probably preaching to people who already have seen this in their own lives and their own plants. So just a reminder for you that the picture on the top right there, if you see that sort of grey-white nondescript deposit, that's classic amorphous silica scaling. You can see a screwdriver there for size reference. But obviously on the top left picture, of course, you can get deposits which just build up until they actually physically block pipes and, you know, restrict flow. And then the pictures at the bottom there, perhaps even the most interesting, the one on the right is from a reinjection pipe, reinjection line pipe. And we call that sort of scaling or deposition, or amorphous silica deposition, we call it fence post type scaling, because it looks like a whole lot of little fence posts that someone has pushed over. And in the picture on the bottom left is actually, we've broken off just a small piece of that fence post type deposition and shown it there. I actually managed to get that picture from, this is from a central North Island, New Zealand plant. And you can see that like it used to be attached to the bottom, attached to the pipework at the bottom showing there. And then you get all these angled fence posts coming up at you. So, you know, you can imagine when you start getting those sort of deposits that they really impact on brine flows, and, you know, being able to get the brine out of the system and down into the reinjection just starts blocking everything up. Thanks, Andrew.
Oops.
Sorry, Pete. Two ahead. Sorry. Okay, so what does it ultimately mean? I mean, apart from having to deal with the silica, which is actually fouling and building up scale inside your plant, which of course will eventually need removal, you know, by one way or another. But apart from that, all the time when the pipes and the formation is becoming silica fouled, you start losing power production. You just can't put enough of the brine, can't get rid of it, can't get it down the ground again. So here's an example. This is published a number of years ago from a central North Island power plant. When they first started, it was producing 100 megawatts. And then, of course, what happened in this particular location is that the actual production field depressurized over time, and there was a decline there. But then, after a number of years, the amount of silica that was building up in the reinjection pipework and the reinjection wells actually really started to impact on the power production as well, to the point that come in July 2007 or so, they actually put in some more capacity, some more wells. But look again, so we have production, nice production for a while, and then it starts tailing off again. And this is due to silica deposition. So, you know, I'm sure in other countries, as it is in New Zealand, like a megawatt of electricity is worth a lot of money over a year. And so if we can minimize or control silica, it's a really big improvement for the operator. So thanks, Andrew. Okay, so let's discuss a little bit so we can get an understanding of silica deposition. So I've got some words on the left-hand side, but I really want to address everyone's attention to the right-hand side over here. So just some chemistry, structural formula, but like when silica dissolves in water, it actually forms, it's actually, we call it dissolved monomeric silica. It's actually silicic acid. And when I say acid, it's only an acid because it can react with caustic, which we'll go into in a moment. But basically, we've got molecules of monomeric silica in the water, and if we go oversaturated, they start holding hands. That's the way I like to think about it. And the higher the oversaturation, the faster they start holding hands, until we end up with polymerized silica. And the polymerization carries on in 3 dimensions, and we end up with silica colloids. So very tiny colloids or suspensions of silica. And then they will then, if they bump into something, if they're carried along in the brine, if they bump into another piece of silica that's already attached to something, they tend to add on. So you get like a binding effect. Starts off with binding to the metal, you know, the metal surfaces in your plant. Then they form a layer of silica, and then the silica just keeps building up. And as long as it's oversaturated, it's going to keep going. And that's why I've shown this picture here. These deposits here, they will just keep growing and growing and growing until such time as there's almost no flow. That's the way of silica, is once it's oversaturated. So again, the takeaway is once you're oversaturated, silica starts holding hands, and it's just a matter of time until, unless the temperature goes up, it's just a matter of time until they'll actually start polymerizing and forming deposits. Thanks, Andrew. Okay, so a little bit more about understanding silica, and this is probably to the people on the call probably well understood, but when silica comes out of solution in a geothermal plant, it comes out as amorphous silica. And that's the solubility of amorphous silica is very temperature dependent. As you can see here, as the temperature goes lower, the solubility goes down, and as the temperature is higher, the solubility goes up. So that's well known. You know, silica has normal solubility, but also there is an effect on brine pH as well. And we do see that as brine pH increases above 7, it becomes more soluble. And there's as clearly shown in this diagram here that amorphous silica at pH 7 is lower solubility than at pH 9. Not that many geothermal brines run at pH 9, but it is a contributing factor. Thanks, Andrew. Actually, pH has another important effect on the whole silica deposition situation. Just wait for it. Thanks, Andrew. And that is pH has an effect on the precipitation kinetics. Now, kinetics is to do with how fast reaction's happening. And I remember Dr. Mike saying, you know, like things happen, like thermodynamics ultimately controls what will happen to a chemical. But how fast things happen can be different to actually whether they can happen and how fast they happen. So we got this a little chart here that was developed, and it shows that like the rate of precipitation of silica depends on pH. It actually gets lower at lower pHs. Actually, and we'll go further, when we go further ahead, we say that some geothermal operators use that to their advantage. But basically, if you can drop the pH, based on this chart, if you drop the pH from 7.5 to 5.5, the reaction rate of silica polymerization, deposition, and precipitation reduces by about 30-fold. So that people, as I say, we can use that to buy ourselves some time. Thanks, Andrew. So how are we going to, everyone agrees that like being able to mitigate or prevent silica scale would be extremely useful. So how do we go about mitigating that? Thanks, Andrew. So I'm gonna look at these 4 areas. I'm only going to touch on a couple of them, but what I really want to get through to is scale inhibition. So those are the four chemical strategies related to silica deposition. We can use acid to delay polymerization. We could use caustic to increase solubility, but that's very expensive and it causes a lot of other problems. So I'm not actually going to discuss that one here. We can online chemical clean the system, and we can look at scale inhibition. Thanks, Andrew. Okay, so acidification. Now, this is used, I'm not sure the people on the call in different parts of the world may know of some plants that you're working in or that you know of that do acidification. Certainly in New Zealand, there's some large geothermal power stations that do acidify. So the idea is they add sulfuric acid and take the pH down to about 5, which slows the silica polymerization process. And by the way, this can also help with like solubility of certain salts of calcium, magnesium, aluminium. But basically, we're just trying to buy time so that the brine, even though it's super saturated with silica, it doesn't polymerize fast enough to cause a problem. It gets back down the reinjection in time. That's the whole idea. Certainly silica deposits, if you follow this approach, the silica deposits are minimized in the generating plant. But it's not easy to engineer because we're dealing with high volumes of sulfuric acid, and you've got to be very careful with the pH control for a couple of reasons. If you dose too little, you'll get rapid silica deposition because you're typically trying to run with high levels of silica saturation, right? And if you dose too much, you can get steel corrosion. So this little chart over here on the left-hand side shows effectively it shows polymerization of silica versus time at different pHs. So for instance, at pH 5, silica doesn't really polymerize fast at all. But if the pH went up to 5.5, there's only a very small change in pH, we get rapid removal of silica. In other words, it's holding hands and it's going to be forming deposits. The other situation to be wary of when we talk about acid dosing or acidification to control silica deposition is, of course, we're pushing all that sulfuric acid down and effectively down into the reinjection formation. And of course, when it gets down there, the brine that you're sending to reinjection will actually pH neutralize with the rocks that are down there. I'm not sure whose network quality that is. Might be yours, Andrew. Hopefully everyone can still hear me.
Yeah, you're fine, Pete.
Is that you? Is it? Okay, Andrew. Okay, but down the bottom here, so we can get pH neutralization in the formation. And if the temperatures aren't high enough where the pH neutralization is happening, that can force silica deposition down in the reinjection well. So what happens then is the reinjectivity reduces over time, and the plant ends up in a situation where you can't get rid of as much reinjection brine as you wish. Thanks, Andrew. I've got a window on my screen saying bad network quality, but I'm not sure if it's you or me, Andrew. Can I try and close that?
Possibly you,
I'll
Pete.
try and, oh yeah, I'll close it. Yeah, I've got control. Sorry about that, everybody. Okay, so mitigation strategy 3 is online chemical cleaning. And this is one of the areas that we've been working on, and Dr. Mike and our own Dr. Logan Muller here in New Zealand, we've been working very successfully. We're having great success with online chemical cleans of like reinjection wells and stimulating those, removing silica from those, and also cleaning the a binary plant to remove fresh silica from those. So I won't go any more. There is actually a webinar available for you to view, available on solenis.com, and certainly I'd encourage you, if you haven't seen that that webinar from Logan, Dr. Logan, please do look into it. It's very exciting and working very well. And in fact, one of our clients here in New Zealand has advised us that the work they've done with us has saved them many millions of dollars to their bottom line by doing these cleans with us. So yeah, that's enough on that one, because I want to talk about silica inhibition. But certainly, if you want to know any more about that, please look at the webinar or reach out to especially Andrew, who's coordinating responses. Thanks, Andrew. Okay, well, I need to speed up. Oh, sorry about that, everybody. I want to leave time at the end for questions. So let's have a look at scale inhibitors. So when you think about it, what a good geothermal power plant silica inhibitor is, well, it would basically would keep your plant clean and free flowing over long periods of time. Obviously, it would be easy to use with no other problems like safety or corrosion. It'd be economical, and perhaps a very important thing here to consider is it would actually potentially allow higher megawatt production. In other words, if you could actually run systems, get more heat out of a brine, you can make more megawatts. So that would be an ideal in the real world. But thanks, Andrew. Of course, in a laboratory situation where we've got to test to try to find scale inhibitors, we of course need a much more shorter term evaluation. So in an R&D lab, which is what Dr. Mike and his team does over there, we can minimize silica polymerization and minimize precipitation of silica. And the good thing about those two is we can actually test to see if it's working, right? If we actually test the silica, monomeric silica versus time, that gives us a measure, is this thing working or not? And the same, or does the test solution become cloudy with colloids and deposits? So that's another good thing we can test. So look, in what I'm going to show you just now, we're talking about the work we did on a synthetic geothermal brine. Obviously, we've got to pick a brine from around the typical brine and then test it as there. So what did we do? We started off and we tested like over 100 commercial and developmental products. So, and in this case, we're looking at a synthetic standard brine. No, an important thing, and Dr. Mike mentioned this, made a good point about this previously. If you do use a synthetic standard brine with no trivalent metals, I'm talking about specifically about aluminium and iron, because we know these things tend to poison inhibitors, and neutral pH. So if you have a look at those charts, just some inhibitors, we just numbered them there. We would look at those and say, compared to no inhibitor, some were actually worse than no inhibitor. Some were a lot better. And some, for instance, these like this brown line, inhibitor 7, inhibitor 8, these ones here, they actually kept silica from polymerizing for long periods of time. For instance, here, this is time across the bottom. So if we can keep silica from polymerizing over like an hour or two, it's a very good indication that would be a useful technology to use in your plant. Thanks, Andrew. But what did we find? And this is where having, our experience, Solenis's experience in the field, and in a focused research and development department. I mean, we're looking for silica inhibitors for geothermal. We're not just taking silica inhibitors that people have developed for reverse osmosis or cooling water treatment and saying, oh, well, it works great in that situation, so please try it in geothermal. No. So we know that most geothermal brines have levels of these poisons in them, like aluminium and iron. And what we found is that when we have a brine, or we deliberately contaminate our test with aluminium, just 1 ppm of aluminium, the performance of these inhibitors just fell away badly. Thanks, Andrew. And not only did the inhibitor performance fall away badly, but in the presence of specifically aluminium, we actually started getting precipitates. So the water is becoming cloudy by reaction of the inhibitor with the brine and in the presence of aluminium. So what we're saying is most of the inhibitors, or all of the inhibitors that we used, standalone inhibitors, they actually were badly affected by aluminium to the point they hardly worked at all. Thanks, Andrew. So what we thought, well, we do need, working with the guys like Mike, Dr. Mike and the R&D team, we said, well, we really need a new approach. We need complementary actives. We've definitely got to condition the problem cations like the aluminium. We've still got to delay polymerization, and we've got to prevent precipitation. So we were, thanks, Andrew, carried out a lot more testing where we're actually using a dual active, and we actually did find a combination that worked really, really well. And that's what you're seeing in these charts here. So we found by incorporating, like using a combination like inhibitor 7 and inhibitor 11 at varying dose rates, we've tried it in lots of different dosages, we could actually prevent, the silica levels just stayed the same over time, certainly over 2 hours or so, and the water didn't become cloudy. So it's very good indication that we're actually doing something well. And I want to point out again, it's because we actually knew to look for the problems that might otherwise be caused by these poisons, especially aluminium. Thanks, Andrew. So, based on what we saw with that combination of inhibitors, and by the way, all that work is actually wrapped up nicely by our Dr. Mike Todd in a technical paper he actually presented to an international conference. So if you're certainly interested in actually getting a copy of that paper, the full paper, just let us know. However, so I wanted to say that this dual active inhibitor is a development product, and it's available for field trials. So we're certainly seeking validation trial sites. And I'd ask you if there's interest there, do contact Andrew or myself or Mike to actually discuss how we might be able to run field trials with you. I did want to point out that we're actually, spending money on a sophisticated testing rig to actually be able to develop guardrails for this approach. And we've got an example of it, a picture of it there. Where we take a flow of a sample of geothermal brine from a customer reinjection system. We can dose chemicals, measure corrosion, cool it down, use a special ultrasonic scaling probe to measure deposition. Then what's special about this particular rig is we then add a retention pipe work to give it time, because remember what I was saying before, silica polymerization takes time. So if we're going to mimic this in a side stream rig, we need to allow time for this to happen. So thank you. So thank you, Andrew. So that's all coming our way in terms of like guardrail development for this inhibitor. Thanks, Andrew. Okay, so then we need to, I just want to finish off, and I certainly thank you for your attention so far. But like, it's one thing having, silica inhibitors or potential silica inhibitors. The other thing is for you to ask yourself, how would I know it's working over a relatively short time frame? Or do I have to wait like spend a lot of money and wait 3 years to know that it did anything. So I want to just introduce a special scale monitoring tool that we can use to actually show you that silica is actually being controlled or not controlled. Okay, so I'm talking about an OnGuard 3S analyzer, but basically this device uses ultrasonic distance measurement. So we take a sample of, if we look at these pictures down here on the bottom right, we take a sample of brine past a test probe. The test probe has a gap between an ultrasonic emitter and a reflector plate, so that anything that builds up on that reflector plate, like silica scale, will actually be able to be measured, and we can get a scaling rate of millimeters per year. Thanks, Andrew. We've actually done some runs with this technology, down in central North Island, New Zealand. So here's a picture after about 1.5 to 2 weeks exposure to the reinjection brine. This is the reflector plate. The ultrasonic emitter is just up here. You can actually just see the start of some deposition happening on this probe, not only on the reflector plate, but all over these little white specks there. But the ultrasonic distance measurement can actually measure it down to micron level. So what we saw is, over time, we just saw a steady, gradual build-up. Of course, because it was a test thing, I was pulling the probe in and out every few weeks, so we got some of this situation. However, we saw that after a couple of months, we had about 150 microns of scale there, and the key thing was that this rate of build-up was confirmed as similar to what the historic deposition rate is for the customer. So we know that this actually gives you a real indication online, as you wish, of silica deposition. Thanks, Andrew. So look, been very quickly through these a few chemical silica scale mitigation strategies, and there's certainly so much more to say, but we're certainly happy to engage with you on an individual basis. Thanks, Andrew.
Thanks, Pete. Obviously, a topic Pete's very passionate about, and as a result, we've probably gone a little long and don't have too much time for questions, but I think we do have 5 or 6 minutes. So if anybody has any questions, we'd certainly invite you to submit those using the chat function. While you're thinking of questions and typing those in, just wanted to make you aware that Solenis has been very active in the geothermal with geothermal global conferences in 2021. And I think we've delivered some 12 papers this year, also including the World Geothermal Congress, which isn't on the screen at the moment, and covering a fairly broad range of topics from scale inhibition, corrosion control, and well cleaning and simulation. So there really are some excellent papers there, some co-authored with some of our customers, and I would really encourage you to seek these out at the association links that are indicated here. So just checking for questions, and at this point we don't have any, so we'll just wait another minute or so, see if anyone comes up. No, still no questions. So I think Mike and Pete, you've obviously covered the topics very well. But if anybody does
I see one. I see one now, Andrew.
Oh, here we go. Yeah. So here's a question. What are the challenges of implementing downhole injection anti-scalant in production well, especially with only small water fraction or shallow water level? So I'll read that again to Pete and Mike. What are the challenges of implementing downhole injection of anti-scalants in production wells, especially with only small water fraction or shallow water level?
Yeah, Mike, you may have some response to that. It sounds fairly atypical to me, and I'd probably have to actually refer to my colleagues, including Dr. Muller, to answer that. But it's certainly a very good question. And the difficulty, of course, is if the water's already coming in two-phase into the production well, then flashing may have already occurred. So it might be very difficult to get an anti-scalant into the area where you need to, where it can be effective. But maybe I didn't understand your question that well.
Yeah, Hendy, we may just need to follow up offline to get some more details with you. But yeah, as Peter said, if it's already two-phase, then that may be difficult and too late. We have worked with some customers in New Zealand in potentially similar situations to stimulate production wells where anti-scalants just aren't as effective. But from my experience, as I showed on that one slide, you definitely want to dose below the flash point to have your best chance of preventing calcium carbonate scale formation. But yep, thank you for the question, and if you'd like, please follow up, and we'll try to address it in more depth.
Thanks, Pete. Thanks, Mike. So no more questions at this point, and we're pretty much coming up to the hour. So I think what we'll do is conclude the webinar. And again, if you do want to reach out to us on today's topic or anything else in relation to geothermal chemistry and treatment of, I've got my email down there, and I'll certainly coordinate any questions or queries, and you can also reach out to us on Solenis.com, and we'd be excited to talk with you. So thank you very much, everybody, for your time. We hope the information imparted has been beneficial, and wish you all a good night, a good day. Thank you, everybody.
Thanks, everyone. Good night. Good morning.
Thank you all.